Okay, so the last speaker this session is Cody Wild. She's a senior data scientist at Sophos and is going to be talking with us about multi-class problems and different misclassification costs. So, Cody, please go ahead.
All right. Hope everyone's caffeination is holding up. I know we're like in the last bit of the hour and everyone's waiting for lunch, so I'll try to keep everyone awake. As Jeff mentioned, I'm going to be talking a little bit about how to design loss structures that work on problems where you have unequal misclassification costs. So, first, a little bit of a fun disclaimer. This isn't precisely the talk I was hoping to give to you all today. This is not scaling properly. Great. This will be fine. So I had previously proposed an approach, and in my initial experiments, I'd seen it perform really well on the data I'd been testing it on. Then, about a week ago, while replicating experiments for this conference, I found a bug, after which performance gain for that proposed method was still present in some dataset sizes, but overall was less consistent than previously seen. So instead of the theme of this talk being discussion of that method and why I think it performed well, it's instead going to be an overview of the different experiments I did, the different methods I tried, and where they performed well or didn't perform well. So all of that feel-good discussion people do about negative results and how they should get more airtime, this talk is very much in that theme. So not sure how the scrolling is going to work, but we're going to do our best. Okay. So something that we know as humans, but that often we don't have great ways of communicating to our algorithms, is that we don't want our model to make mistakes, right? Like, we would love it to be a perfect classification model. But in practice, it's going to make mistakes. But some mistakes might be worse than others. So the theme I'm going to be talking about for this presentation as a whole is website classification. So recurring examples will come from that domain. So misclassifying a weapons site as being a children's site is much worse than misclassifying it as controlled substances. And intuitively this makes sense, right? Because what humans do with this decision is to implement certain rules or policies on top of it. And the policy that one might implement for controlled substances is likely to be pretty similar to that of weapons versus, showing this at a kindergarten and then showing them a bunch of AK-47s might lead our customers to be a little bit concerned. So often these costs are known a priori, at least in some form. They may not be known perfectly quantitatively, but they might be known ordinally, that some things are worse than others. And we may want to build a model that is guided by that information. So let's dive into cross-entropy. Cross-entropy is one of the most commonly used loss functions in neural networks. This is partially because its gradient flow plays really nicely with softmax activations, which are commonly the output layer of a neural network model. So you end up with this distribution over probabilities for all of the classes, and cross-entropy leads to gradient being able to flow through that softmax really well. But it also has some downsides. So here you can see the formula for categorical cross-entropy. So categorical just means there's more than one category as opposed to binary cross-entropy. So for each example, we sum over all the different classes and multiply the true probability of that class by the log of the probability that our model output. Again, the softmax can fairly roughly be seen as a probability. If there are no Bayesians in the audience, you're going to throw things at me for saying that. But a thing you can say there is that if you're using 1-ha labels, then the YC, the true probability of the class, is going to be 0 except for your true class. So in practice, all this is doing is saying, hey, let's jack up the probability of the true class. I don't really care what happens outside of that. And so you can see this plot, the orange kind of disappears below the green at a certain point, but that represents the true Y value, which is basically being used as a mask on your log probabilities. So that only actually is different than 0 for the true class. Anything else that happens outside of the true class, your loss function doesn't really care about. And so this is like a little bit suboptimal for the problem framing that I was showing earlier, where it matters where else we put our probability mass. If we have as our first guess that it's a children's site, but our next best guess is weapons, that's a lot worse than a lot of alternatives our model could do. And we can't specifically weight that probability differently. So this is an existing approach in the literature, which is a bilinear loss, and I'm going to be referring to it as that throughout the talk. This is proposed in 2017, a paper by Resheff et al., and it's actually a combined loss, where it's a convex combination of cross-entropy and a bilinear loss function. So you can see these two up here. These are actually the log and non-log variants of this, so the paper proposed both. The methods in my talk mostly use the non-log version, but I'm just going to go through the non-log version, and then you'll kind of see what the log version is doing. So A here is a cost matrix for misclassification. So each row shows the costs of misclassifying, something when the true class is, 0, for example. Here are all the costs of misclassifying it as all of the other potential classes. And so by multiplying the true YT by this matrix, you pull out the row corresponding to the true class. So you pull out that row, and then you multiply it just by the softmax. So you're basically just taking a dot product between the weights for each possible class for this specific true class, and then scaling up your softmaxes by that, and presumably you have 0 cost associated with correctly classifying something. So then you have positive loss values associated with classifying it in many different wrong ways. So in this plot, this is a simplified version where you imagine there is actually like a uniform cost across all different misclassifications, just for visualization purposes. And you can sort of see this works in an inverse way to how the cross-entropy loss works. Here, since you're downweighting the probability of bad things rather than upweighting the probability of good things, you have 0 contribution of your true class and then contribution from all your other classes. And then the difference between log and the linear versions is basically just, the log version is going to care a lot when your probability of the incorrect class gets high, and it's going to care less. So again, here it's doing a log of 1 minus the probability of all these incorrect classes. So this is just kind of working as we would expect a log term to do, and it cares less as you get to like very low probabilities of the bad classes. It's going to care less about that, versus the just straightforward linear thing is going to care the same amount at any point. And I only mostly did experiments with the non-logged version, but you could theoretically try the logged version as well. And this is the proposed alternative that I had initially suggested for this talk, and I'm going to walk through it. It's a little bit odd, but once you get the gist of what's going on, pretty straightforward. I'm calling it clustered cross-entropy loss. So here I basically take the cost matrix and cluster it so that you have hierarchical clustering, so that things that have lower costs for being misclassified as one another are going to be more likely in the same cluster. And you can create from this different granularities of labels. So you can conceptually imagine that you have one granularity that is like your full scope of labels, maybe another one that if you squint at it and make up names applies for like legal, illegal, and then a broader one that's like savory, unsavory within the legal category. I'm making these things up and applying them to data, but you can kind of imagine that these would be the sort of things that come out. And then what you can do is just perform cross-entropy over these multiple different labels at once. So you could say, well, I want you to get it in the true class, but also I want you to tell that it's legal versus illegal. And also I want you to tell that it's savory versus unsavory, for example. So the intuition behind my trying this approach in the first place was that they're all cross-entropy losses. And so they're all going to be on a more similar scale to each other than like a bilinear loss, which when you have a lot of classes is going to like vary a lot more wildly in terms of the scale of it. And so my thought was that it'll be easier to do like hyperparameter optimization on this than it would be on a bilinear loss. So let's just dive in again, because there's a lot of math and it's still a bit early on a weekend morning. So I have some colorful diagrams to make it a little bit more straightforward. So let's imagine we have a 3-class world. There are only 3 classes, children's sites, weapons, and drugs. And then we're imagining a loss function taking in 2 possible model predictions. The top one's A, bottom one's B. And you'll note both of them place the same probability on the true class, which in this case is weapons. But they divide their alternative probability mass onto the different classes differently in these 2 predictions. So as we mentioned, cross product is implicitly taking a dot product between the negative log probabilities and this 0-1 mask that is just your one-hot label. And so, as expected, these have the same loss for both of these predictions. Alternatively, if you imagine a bilinear case, its kind of mask, if you want to use that term pretty broadly and loosely, is instead the misclassification cost for this middle row where the true class is weapons. And so we say, when it's really weapons, then the cost of classifying it as children's is 5, the cost of weapons is 0, the cost of drugs is 1. And then we just take a dot product between that and the softmax probabilities. And so you see here, as you would expect, because loss A puts more weight on the high cost class, this has a higher loss than the case where we put most of our mass on a low cost misclassification class. And you see a similar thing happening, though, through kind of a different medium for the clustered cross-entropy loss. So let's imagine in this case, I think not unreasonably, that if we clustered this, you would get one cluster corresponding to children's and one corresponding to weapons and drugs together. And so then this is what these vectors are here. Here is kind of the auxiliary losses true label function, because it is in this weapons or drugs class. And then here is just the aggregated softmax. So this is just kind of combining the softmax probabilities for the two items in the cluster together. And here again, A and B. The top one's A, the bottom one's B. So if you look at loss A, this first term is the exact same as the granular cross-entropy, because that's exactly what it is. And then the second term is the cross-entropy using this clustered loss. So in the first case, you have 0.4 probability on the correct cluster, and in this case, you have 0.9 probability on the correct cluster. And so as you would expect, you see lower loss in the case where I put more probability on the correct cluster, even though I put the same probability on the correct specific label. All right, so enough of kind of theoretical background. I'm now going to dive into some of the specific experimental work I did and draw out some of the conclusions and some of the, I think, still initial theories about why those conclusions hold. Let me get some water. All right, so I know that this graph is not particularly easy to see, and it's kind of just mostly meant to intimidate you, which is to show you how many classes we had and how unequal the class distribution is. So you can, if you squint at this line here represents 50% of the data. So 3 of our classes make up 50% of our training set. And as you can see, we have this kind of very long tail of small classes. So this is just something you might expect about the web, right? Like lots of the web falls into these broad categories, and then there are these very niche things we care about, but that are pretty low probability. Another thing is that you have a lot of data, but actually human-assigned labels are pretty hard to come by for like annoying and complicated reasons of it's not being all that legally safe to just show people random parts of the internet and have them label them. So often you have a lot of unsupervised data, but not that much supervised. And our team's working on doing some semi-supervised work, but for the moment, a lot of my tests are going to be at kind of low data set sizes, and that's motivated by the fact that our number of training examples that are labeled is actually kind of hard to come by. And as has been mentioned, and as you can realize, there is this problem of unbalanced cost of misclassification. Again, this is kind of just to give you a sense of what's going on. Don't have to try to squint at it. But these are all of the different classes in the true classes, and these are all of the different classes that could be predicted as. And you can see that there are these varying colors of like how costly these misclassifications are. And this came from the domain experts on our team, the people who actually sell this to consumers. One note is that this is pretty ordinal. They're all numbers from 1 to 5. And the domain experts don't necessarily have a sense of, yes, this one is 3.6 times worse than this one. So one thing we try later on is trying to like change the actual quantitative scaling to see if that changes things. But this still does give us something we can work with quantitatively, even though it's ordinal. And then I'm not going to focus a ton on this because I'm mostly focusing on the loss function rather than the actual underlying model. But just so you're not totally in the dark, our inputs here are URIs. So these are uniform resource identifiers for places on the web. And then the model we use is the Sachs et al. Model, 1D convolutional model over this. So we embed the characters, we run a 1D convolution over them, and that's our base model, and that's used for all of these different experiments. And the 2 baselines are what I call vanilla cross-entropy and then observation-weighted cross-entropy. So this one, as you might guess from the name, doesn't weight the specific mistakes, but weights the observations based on the average misclassification cost of the true label. So it doesn't say how bad is the specific mistake the model is making right now, but what is the average of all the possible mistakes the model could make? Because, for example, extreme or illegal things have high cost of misclassification into basically every other category, versus business has pretty mediocre cost of classification into everything else. So you might imagine this is like a simple way of trying to incorporate the same information. And a fixed test set was used for everything, just to avoid any confusion there. So the first question that we might want to ask, and it's kind of the most central question, is, do you actually see a reduction of your more severe mistakes with these misclassification methods? And I'd like to separate out 2 ways that you can reduce the number of mistakes in severe categories. One is obviously by just reducing the aggregate number of mistakes. If you reduce mistakes everywhere, cool, great, you've solved the problem in a certain way. But I'm actually sort of more interested here in saying, how does the model trade off different kinds of mistakes? So sort of for a fixed aggregate error rate, how does it divide the errors that it's making? So I don't show here, but at very low training set sizes, neither bilinear nor clustered methods performed super well. And my intuition for this is that they're both kind of adding a little bit of regularization and making the task a little bit less straightforward to learn. And so at like very low data set sizes, that's like a little bit too strong of a regularization effect. If you look at this left-hand plot, this is with a 25,000 training set size, and the green bilinear loss is what I'd like you to take a look at here. And so here you see this effect where you actually have more, in relative terms, mistakes at 1 and 2 severity levels, but then fewer mistakes at a severity 3. And so you kind of see this dynamic where more so than other models, bilinear loss is taking on more hits in this low severity region and then less of them in the high severity region. You then see clustered loss, which kind of doesn't really demonstrate this trade-off properties, but at high data set sizes does seem to actually have lower aggregate mistakes. This is just kind of, I'm going to just jump past this because it's not very interesting, but this is just the zoomed in version of the end of those plots. Another question you might ask is, how much does the overall performance trade against this reduction of severe mistakes? So in the original bilinear loss paper, they actually showed that upping this coefficient on bilinear loss means you trade off for fewer bad mistakes, but your overall performance goes down. Interestingly, we didn't actually see that. Bilinear performs pretty consistently well at aggregate F1 scores across the whole data set, or it performs better or equivalently depending on where you are. At 100K, you do start to see clustered loss performed better in aggregate. So my theory is that it's giving some information to the training process, but that information doesn't really come out until you get to high data set sizes. I'm going to skip over the uniform thing, just because I don't think I have time to dive into that right now, but I can go over it in questions. Again, remember bilinear loss is a convex combination of bilinear and cross-entropy. So increasing alpha means more of our loss is the bilinear part rather than the cross-entropy part. And sort of pleasingly, you can kind of see this effect happen here, where the red is a very low alpha, and here you have many more high-severity mistakes and many fewer low-severity ones, versus the brown, where you again see the stronger trade-off, where it's pushing its mistakes to be on the low-severity rather than high-severity side. Interestingly, doing a balanced combination has overall aggregate performance that's the best, so you kind of need to trade off these two things if you were deciding an alpha to use in production. Also going to jump over these. These are some things that we did that didn't really have interesting results. So we tried them. There wasn't really a story there. We tried aggregating up the weights by 5, since again, these weren't raw quantitative numbers, to see if we could accentuate this weight. Didn't really change anything. We looked at training curves to see if there was different loss or different speeds of training, and didn't really see that. So, wrapping up here. What I took from this overall project was that there is evidence that using loss functions that take into account misclassification costs can not just shift errors to places we might prefer them happen, but in some cases can also actually improve aggregate performance. In terms of shifting errors to low severity regions, we found that the bilinear loss method currently in the literature does the best job at that. But that there does seem to be some possible information injecting effect of both, including the clustered loss function at these high data set sizes. I'm just going to kind of end on this slide, which has some remaining questions that I've been thinking about, which is, to what extent are both of these losses acting sort of like a ground truth model distillation approach? So if you are familiar with model distillation, it's the idea that you train a model based on the probabilities generated by another model, and this is meant to give your new model a sense of what are the things that are closest to this, what did the old model think that this was going to be most like? And so here we're kind of ground truth injecting that in, where we're telling it, hey, implicitly these things are close in some sense, even if that's only in the response we might have to them. Also, again, I've only been doing this, fixing this kind of talk in the last week, so I'd like to try the clustered loss on much bigger data set sizes to see if this pattern of it performing well continues. And also try varying the weights on the different granularities of the clustered loss. And this is all on one data set. So these conclusions are a case study. They're not a prescription that it'll work well everywhere. And with that, I'd like to thank you all and open up to questions.
Great, thanks. Okay, so one thing, Cody, I'm curious about, in the bilinear case, there's kind of the matrix that you can set, right, the weights to say how much you want to penalize one misclassification over the other. And is that missing in the clustered approach that you have, or how would you try to kind of, or does it make sense, do you think, to try to get that notion into the the clustered mechanism that you've created?
Sure. So the matrix is implicitly, though not directly, present in the clustered case because that is where the clustering is derived from. And so you cluster it using that that A matrix that you'd use in the bilinear case. And so it's in some senses a much coarser and less precise way of representing the matrix. So instead of saying, here are the exact, like this one has a 1 misclassification with it and this is a 2, it's more like these are all together versus not together. So you're representing the information, but it's representing it in a kind of broader or coarser and less finely grained form. I said the same thing 3 times, sorry. So yeah, I mean, that's kind of what the approach is. And so I think that's one of the things you're kind of trading off, where you're saying, I want to represent this information, but do it in a kind of broader way.
Thank you. That was a really cool talk. In the clustering loss function, you mentioned using hierarchical clustering. Just a quick clarification point. Are you picking a single level of resolution in the hierarchy for your computation, or are you summing over all levels of hierarchy, and is the loss like, that kind of sum over all possible resolutions?
Sure. So for these experiments, I had the granular labels, and then I had 2 levels of granularity on top of that. So I think that there were 60 granular labels, and then I think 12 and 7 in the other categories. And I sum over all of them in a weighted way. So I take the cross-entropy. Basically, if you pretend each of those things are their own loss function, it's a super vanilla cross-entropy. And then I just sum those cross-entropies and I weight them. I think here I used a 0.7 weight on the granular and like a 0.2 and 0.1. But that, again, that's one of the things I want to test as a hyperparameter. Yeah, always more hyperparameters.
Thanks. Yeah, that was really interesting, and I'm sure that I did not follow all the fine details. So this is kind of like a high level, like, does this intuitively make sense question. In terms of the clustering, the misclassification losses, would it be sort of intuitively equivalent, or what would the difference be between attacking the problem that way versus doing kind of a sequential hierarchical clustering, where, say, at the highest level, maybe you treat weapons and drugs as sort of within a cluster, and you do a first stage where you try to classify between children's versus that cluster, and you have a straightforward cross-entropy loss measure, and then a next step down, do kind of a similar thing where you're trying to categorize within the initial cluster.
Yeah, I actually had some early experiments that were not exactly doing that, but doing something similar to that, because I think it is a really good idea and an interesting question. And that what I was doing was basically doing like curriculum learning over the span of training. So doing a soft version of that, where in the beginning most of the weight is on the like really granular clusters, and then later on it's on the kind of like, in the beginning it's on the like very broad clusters, and then later it's on the more granular ones. I didn't get to redo those experiments after fixing the bug, but I do think that that would be a really interesting thing, and I might try to do that before I post the blog that will accompany this talk.
All right. I was really interested. I was wondering if you had any intuition or thoughts on how what you're proposing here, sort of how that compares to like a traditional multi-label paradigm, where you would be learning 2 objective functions simultaneously, and then either add or otherwise combining.
You're asking how this compares to a multi-label approach in which you have multiple things you're learning at once. Well, I mean, I think, like in some direct sense, having multiple labels, you kind of are having multiple labels. They're just derived from the same underlying label, and that's kind of what the clustered loss is doing. Is you have your label that's, again, to make up terms, granular, like legal, illegal, and like good, bad, or savory, unsavory. So you can think of this as kind of being multiple, very non-orthogonal, because they're all derivative of each other, labels. So I think for me to better understand your question, I'd have to have a sense of like what kinds of multi-labels, what kind of different multi-label approaches you'd be proposing. So I'm happy to talk with you offline, but I think I'm going to get a better sense of what you're asking. Yeah, and I'll repeat it.
So from a cybersecurity perspective, for like website classification, one of the best practices I've seen in the field is blocking uncategorized websites. So from an impact to customers who are using this data, is uncategorized an option for this classification model? And did you, in talking with sort of the SMEs who were interacting with customers, was that something
Yeah, it's a really good question. Is asking if we had uncategorized as one of the options in our model. And I think that's a little difficult because there are things that are uncategorized because they're confusing to analysts, and there are things that are uncategorized because the analysts only have so many hours in the day and they haven't gotten to them yet. And most of our things fall in the latter category. And so we could have just added that in and then tried to do a supervised loss with just like basically no data we don't know as a label. But I feel like I'd worry that that would like be confusing or something, because it would kind of imply these are all in one class with shared properties when they're really just things our analyst hasn't gotten to. One thing that I think might potentially, had the clustered loss worked better and more consistently, one of the hopes I had for it was that you could have sort of uncertainty losses in the granular case. And if something was really uncertain in its granular prediction, you could say, well, I have no idea what specific label it is, but I at least think it's like probably legal. And so I think that that was one of the hopes, and I'm not sure if that's actually a productive direction to go in, given that there was shakiness in the performance overall, but that was certainly one of the hopes. So. We do more time?
So class imbalance during training is always terrible, right? And then what's even worse is we assume the distributions where we actually care about inference are even crazier way off. So did you do any analysis on how these techniques work when you need to go apply on some completely different distribution?
I did a little bit. So the version of that I did was basically, how does this work on a uniform distribution, which is a little different than your question, because I think no one believes that the uniform distribution is more like the actual deployment context. But I mostly wanted to know it just as a ground truth of how much of these methods' performance is reliant on the fact that you have this very asymmetric distribution. And this is one of the things I sort of jumped over really quickly in the presentation. But in the uniform case, you do see that the kind of aggregate performance gain you get from bilinear does degrade a bit. So it might be that the initial conclusions of the original bilinear paper, which showed that you kind of trade off overall performance gain against severity reduction, is more true in the uniform case. And that the only reason we're getting this aggregate performance boost is some function of the fact that we have this really unbalanced data set. I didn't try simulating possible deployment sets because I'd just be making things up. So I mean, you could imagine kind of having some parameters of well, we think that a general business is going to be 50% of our data plus or minus 15 or something, and then do strange resamplings. And we could do that, but I don't know that I'd want to hand that to an analyst and say, here is a better ground truth, because it's still just a thing I made up. But it would give you some sense of stability at least. It might be interesting to try.
And you said you were doing 1D CNN on URIs, which I'm a big fan of. I'm questioning, do you ultimately render out a classification decision at the URI level or at the domain level?
We tried both. That's a thing where, in terms of the deployment of this project, we're kind of experimenting with that, and that's also a question of what is visible to our model when it's passed in terms of the actual engineering side, and that's kind of still up in the air. So we're playing with classifying both, and which one we end up using will kind of be determined by that more than it will be by us.
Cody, I actually have a question, and it's a bit naive, but it's about how to. So I feel like when you want to engineer a model to achieve some specific outcome, say I want to classify it at a fixed false positive rate. Mm-hmm. The dual problem is to set weights on classes between trues and false, right? Have you thought about how to optimize, at least in the bilinear case, that weight matrix to achieve sort of get at the dual of the objective problem? You get what I'm asking? It's a very poorly formulated question.
I am currently trying to recall the blog post I read on dual problems when I was looking at the Wasserstein-Gann, and I am not recalling it on stage. But I'm not totally sure how you do that. I'd be interested to talk about it. And I don't know that we have a specific especially with the multi-class problem, we don't really have a specific false positive rate, and it's also a much weirder false positive rate because we don't really care about necessarily specific category categorization, but we might care according to some assumed policy. So if we assume there's a policy that takes all of the vaguely benign things and then blocks everything else, our actual false positive would be what things do we put in the aggregate category of all blocked categories? So I think it's interesting, but that kind of objective hasn't really been communicated to us, so it hasn't really come up.
Great. Thank you very much. Let's thank Cody again.
Does someone else?